Hi everyone, my name is Matt Eubanks, and in this presentation I'm covering a fuzzing paper called Darwin, Survival of the Fittest Fuzzing Mutators. The big theme of this paper is in coverage guiding fuzzing we spend a lot of time thinking about which inputs to fuzz, but Darwin argues that an equally important lever is how we actually mutate those inputs, specifically how we schedule mutation operators during the fuzzing process. So even if you have a great queue of seeds, if you keep applying the wrong mutation operators at the wrong time, you'll waste tons of executions producing inputs that don't even actually explore anything new. So a lot of times this mutator selection is just as important as the actual seed selection. So let's get into this. So on this slide we have kind of a diagram of a general classic coverage guided mutation fuzzing loop, and this is kind of the baseline loop, and then everything Darwin does is basically a small change to this pipeline. So starting off, we maintain what's called a seed queue, and within the seed queue are these inputs that previously did something useful. And so we pick one of these seeds, then we mutate it, and we execute the target program with this new mutated seed. This process produces some sort of feedback, which is usually an expansion of code coverage, like new edges discovered in a graph or new outputs discovered, or it can actually produce a crash, which is even better. But basically, if this feedback is interesting, which means it either increased coverage or triggers a crash, then we can save it back into the queue and kind of repeat the whole process over again. So this whole cycle is it's basically a feedback-driven search process, and it's just repeatedly taking these seeds, mutating them, and seeing if we get any good outputs from them. And when you think about coverages and crashes are obviously much better and more interesting, but coverages, or increase in coverage, is also super important because it kind of gives you little incremental learning about how the program works and can maybe lead you towards a crash eventually. So if we take a step into that mutate stage in the loop, there's actually a lot more going on than it may seem. So fuzzers don't just have one kind of mutation. AFL style fuzzers actually have multiple mutation stages, and one of those stages is called havoc, which we kind of have pulled up on the screen right here. So what havoc is it basically takes an input and it applies a stack of random mutations to it. So these mutations can be anything from bit flips to byte overwrites, insertions, deletions, arithmetic changes, and there's probably some other ones, but it's chaotic on purpose, and it produces a huge variety of candidate inputs. So it's basically taking that input from the seed queue we were talking about and doing a bunch of random stuff to it to try to make something new that we haven't tried. Now, a common baseline in certain fuzzers is just random choice of mutators, or sometimes a distribution of mutators and kind of trying certain ones a certain amount of time. But Darwin actually argues that there's better ways to do it, and that's one key thing that we're going to talk about throughout this presentation is called mutation scheduling, which is kind of the logic behind which mutator gets picked and how often it does. And so maybe something to kind of think about in this context is, let's say the target that you're fuzzing is a file parser. So do you think that a random insert or delete is good for this, or do you think there's something kind of more mild or more targeted mutation that is more structured and will get you deeper into the target faster? So those are kind of things to think of, but we'll keep that in mind. So what problem does Darwin actually solve? So these 3 points are kind of the whole motivation behind this paper and Darwin fuzzing process in general. So first off, the best mutators depend on the target program itself. Different programs have different structures, different fragility, and different input constraints. So a mutator that works great in one target might be completely useless and inefficient for a different target. Second, the best mutators change during the run. So, for example, early on in the fuzzing process, you might want a more broad exploration that kind of explores a lot of the code on a basic level, but then later on, you might need a more specialized mutation in order to kind of get down into those deeper levels, more complicated levels, and explore more of the code. And third, it must stay fast and low tuning. So a scheduler that's smart, but it slows down execution is just inefficient, and it can cause a net loss of functionality, because fuzzing itself lives on such huge execution counts, and a crucial part of that is being fast and working through those huge execution counts fast. And if the fuzzing process requires a ton of hand-tuned parameters, then it just doesn't make sense and won't be efficient at all. So the whole goal of Darwin is basically adaptively learn which mutators to use online with minimal tuning and without killing throughput. So we can go back and kind of take a look at this process and take a deeper look into each one of its steps. So step 1 is choose a mutation according to some probability distribution over the different mutators. Then in step 2, run the instrumented target. Step 3, use the feedback score, which is new paths or new coverage of the code, and we use this to measure how successful that distribution was. And then step 4 is update the distribution for the next iteration of the fuzzing. So the fuzzer is doing the whole input, mutate, execute, feedback, but the Darwin system adds another layer of mutator distribution, getting results from that distribution, and then updating the distribution of the mutators to make the process more effective. And the whole important detail of this is that this is all done during the fuzzing process, and it requires no offline training or anything like that. So after looking at that process and the logic behind Darwin's system, we can kind of see what it's trying to optimize. So we have this set of mutation operators such as bit flip, add, delete, overwrite. Those are just a few examples, but there's many more. And Darwin wants to learn the certain probability distribution over all of these mutation operators that maximizes the rate of discovering new code coverage and new paths within the code. So it's going through, like we said, testing these mutators, receiving feedback from each one of them, and then altering to try and find this sweet spot of the golden distribution that maximizes the efficiency of the fuzzing process. So another kind of key concept is that Darwin is not actually trying to invent new mutations throughout the process to try and test, but it's actually just trying to use the existing ones as efficiently as possible. So let's take a look at how Darwin actually updates the distribution within the mutation process. It uses an optimization method called evolution strategy. And maybe you're seeing the connections now between the name Darwin and the method it uses. It's kind of similar to natural selection or evolution. So here's the idea behind it. You have a current best guess distribution, which is the parent. From that parent, you generate a few slightly modified versions, which is each of the children. Now, each child is tested by running the fuzzing process using that child distribution. And you can see how much new coverage you get from each one of the children. Then, after the evaluation, you keep whichever child performs the best, and then it becomes the parent for the next round. So you're basically trying these small variants and then keeping whichever one's the best and then repeating that process over and over again. So this evolution strategy is pretty lightweight compared to some other mutation methods. It doesn't require gradient information, and it can be pretty robust under noisy or overwhelmed feedback. There are some other methods, including machine learning, which is like in a lot of AI, or reinforcement learning, but these methods are typically a lot heavier and more complex and have more parameters and can be pretty fragile and specific. And this evolution strategy is pretty flexible and lightweight compared to some of those. So we talked about the whole parent to child distribution loop. But the thing about that is Darwin doesn't just keep one parent distribution cycle. It actually keeps multiple parents and multiple sets of children, as you can see here on the screen. And here's just an example where we have 5 parents on the left side of the screen, each one producing 4 children. And the way that the parent produces these children is just by a small tweak that can be as subtle as just a single bit flip. So after making that small tweak to each one of the children, it evaluates each child by how many new paths it discovers or how much new code it discovers, and then it evaluates each one and picks the best. And the reason why Darwin uses multiple parents instead of just one parent that creates children and loops over and over again is because these fuzzing systems can often have local optima, which is like a solution to the target that seems like it could be the best in a local setting, but it's not actually the best overall. So multiple parents kind of allow parallel exploration and exploration of multiple regions of the space at one time. So broader exploration and a better chance of finding the optimal solution. So you may be thinking, why can't we have 50 parents or 60 parents, or what's the downside of increasing the number of parents or children that we have if it just explores more of the space? So more evaluations technically means more overhead and more time spent testing the candidate schedules rather than doing the fuzzing itself. So there's a lot of time spent actually doing this parent-child process instead of just trying to find the best solution in the fuzzing. So there's kind of a sweet spot between the number of parent-child processes and the efficiency of the fuzzing itself. So for each parent, you test each child and then pick the best performing child based on code coverage, and then the best child replaces the parent for the next cycle. And so you can kind of see how over time this process continues and repeats over and over again. The best performing child replaces the parent, creates more children, and you can kind of see how over time each lineage is evolving towards the mutation schedules that produce the most amount of code coverage. And that's kind of how you find this golden ratio and this sweet spot distribution that helps fuzz the code the best. And the coolest thing is that this whole process, this whole evolution process is so lightweight and simple and not overcomplicated that it happens during the fuzzing process, and the fuzzer can still work through large amounts of trials very effectively without being overwhelmed by a super complex process. One of Darwin's most important design decisions is how we actually represent a mutation schedule within the system. So the first option to this is a real valued vector where each mutator has a weight to it, and you can add Gaussian noise to tweak it in relation to the other mutators. So it's very flexible, but it requires fine-tuning of parameters, like for example, how strong should we tweak each mutator in comparison to the other mutators. The second option, which in the paper it says is more practical and more robust, is binary encoding the mutator schedule. So for each mutator, it's either a 1 or a 0. So it's either enabled or disabled. And this is a lot simpler. It reduces the amount of knobs you kind of need to tune. And overall, it's just less work, a lot easier to understand what's going on. So what exactly do you lose by doing binary? You just kind of lose some flexibility and nuance in weighing the different mutators. So you can't really say, oh, let's use mutator A 30% and mutator B 12%. It's more like we're either using this mutator or you're not using this mutator. So you lose some of the flexibility, but it's much simpler, much more robust, and easier to understand what's happening. Now that we know the overall intentions of the Darwin system, does it actually do what it's supposed to? Does Darwin actually change its behavior in a meaningful way, or does it just converge to something close to uniform and kind of just call it a day? So we can kind of look at these graphs here, and this slide is showing mutation history over time and how much a mutator contributes as the run progresses. So in each one of these kind of colored slices represents a mutator, and then you can see the share it has on the overall mutation process. And the overall takeaway here is that if you look at Darwin's mutator usage patterns, they shift pretty drastically over time. You can see it's pretty wavy, it's pretty messy. The different shares are constantly fluctuating, going up and down. Some mutators are getting more coverage share, some are getting less, and it's really adapting to the target's needs at different phases in the fuzzing process. And in contrast, if you look over to the AFL chart on the right, the colored strips representing the mutator shares are much more linear. They don't fluctuate that much. They're kind of being used the same amount throughout the whole process, so it's not really adapting to what the target needs. So with Darwin, you can kind of see that certain mutators become more useful or less useful at certain times depending on the part or the time of the fuzzing process and kind of what the target calls for. Now we can look at the main performance evidence, which is coverage over time, measured as how many unique paths can a fuzzer find in a certain amount of time. So each plot shows time on the x-axis and paths on the y-axis, and it compares Darwin to other fuzzer baselines like AFL and different scheduling approaches. The key pattern in these plots is that Darwin often has a steeper early climb, meaning that it discovers new behavior faster, and it has a higher final plateau, which means it ends up exploring more of the program than these other techniques. So if you look at these graphs, you can see Darwin is the blue, and it's often off to a much faster start in the beginning, and it ends higher on average than the other techniques. But it's also important to note that fuzzing results can be noisy and no fuzzer wins every test. So the correct takeaway is that Darwin won't always win. It won't always be the most effective system, but it's consistently competitive with the other methods and other schedules, and oftentimes, on average, it will improve the path discovery rate. Another measure of performance we can look at is bug finding speed. So the coverage is great, but ultimately the end goal of fuzzing is to find bugs in the program. So the paper also shares some benchmarks on the ability to find bugs. This heat map here is based on a magma benchmark, which is the amount of time it takes to find bugs in a process, and this heat map kind of shows that correlation. So the dark blue is the lower times, which is better because you're trying to find bugs as fast as possible, and the gray means that the bugs were not found at all, and then the red is obviously the higher time to find the bugs, which is not as good. So again, we can see that on average the Darwin method is more blue, darker blue, less red, less gray than some other methods. And like I was saying before, it's not always going to be the best. Some cases other methods might outperform it, but on average, based on this heat map, we can see that it does have very competitive bug finding speed. Like we mentioned before, a smart scheduler isn't useful if it makes the fuzzing process too slow. So the paper also takes a look at the practicality of the fuzzer, the overhead it costs, and the throughput or executions per second that it creates. So the key idea with the trade-off is that you can be extremely fast and produce a bunch of executions per second, but a lot of those executions are just junk and, mutations that aren't going to find those deep paths within your code. Or you can be a slightly slower fuzzer that doesn't produce as many executions per second, but produces much more higher value inputs that can help find these code paths and find these bugs. So Darwin is designed to be relatively lightweight. it has those small 5-parent, 4-child evolution populations. It has very simple tweaks to the children to find those distributions, and it has a representation that avoids all this extra tuning and preparation. So this helps to keep this overhead much more manageable, and it keeps the executions per second relatively close to AFL, which we can see in this table here. Most of the execution numbers are right there neck and neck with AFL, and they're going to be much more higher value. So some of the key takeaways here. First off, mutation scheduling is a real lever. Even with the same seed queue, choosing better mutation operators at better times can noticeably change the fuzzing trajectory. Second, Darwin shows that you can use a simple evolution strategy to adapt schedules online without turning the fuzzer into a heavyweight, complex learning system. And third, the reported gains show up not only in coverage curves, but also in bug finding speed on benchmarks. This means it's not just more coverage, but it's actually better at producing results. So overall, Darwin is a pretty cool example of a fuzzing improvement that's both practical and effective. It focuses on a specific part of the pipeline, keeps tuning minimal amounts, and still produces measurable benefits.